So far, we have discussed about the electrostatics of point charge, a system of charge, and dipole. And we talked about electrostatics, okay, in which we talked about potential energy, electric field, force, and so on. But the electrostatic part, where the charges are not moving, okay. So now we will cover the situation when charges are not moving inside the conductor also. Okay, so we are not talking about the movement of charge inside the conductor in electrostatics of conductors. Okay, so we are studying conductors, but we will only touch upon those properties which says that the charges inside the conductor are static, not moving, right? And we will discuss it one by one. We talked about conductors and insulators in the first chapter, okay? And here what we'll focus on that, conductors contain mobile charge carriers. Conductors has that inside the conductors there are small charge carriers, okay. It can be different entities, but for example in a metal, these charge conductors are electrons. So in a metal there are extra electrons, or we call it free electrons, which help charges to propagate inside a conductor. So what are these free electrons? Actually, electrons are attached to atoms. We know that atom, and inside the atom the nucleus is there, and electrons are attached to this nucleus, okay. And there are many orbits, okay. So let's think about the electrons in the outermost orbit, which is not that strongly attached to the nucleus, because this force between the nucleus and the electron is inversely proportional to the square of the distance, right? So if it is the outermost orbit electrons, which is very far from the nucleus, that will have very less bonding with the nucleus, and that's why what happens, they can easily be detached from the atom, and then it becomes free electrons, and then they freely move inside the metal. And these electrons are free within the metal, but not free to leave the metal. So they are free, but they cannot just leave the metal. They will be inside the metal, but they are free from their atoms. When they were attached from their atoms, they are no more attached to their atoms. Okay, that's why they are called free electrons. Now the free electrons form a kind of a gas. They collide each other and with the ions, and they move randomly in different directions. That is called drifting, okay? In an external electric field, they drift against the direction of the field. That simply means that if there is external electric field, so when we say external electric field, we are talking about the source charge is positive, okay, and because of this there is an electric field, and the electrons are negatively charged, so the direction of the electric field is towards right, and electrons are negatively charged, so there will be attraction force, okay. Because of this electric field, it will move in opposite direction to the electric field. So this simply means, when I say that in an external electric field, the electrons drift against the direction of the field, okay, in opposite direction. So far whatever we have learned, so there are certain results, and especially about the metallic solid conductors, okay, and there are 6 such results that we need to focus, and we will deal it one by one. The first one is, inside a conductor, electrostatic field is 0. let's draw one conductor. Okay, so this is our conductor, and there are a number of free electrons inside a conductor. Okay, that is the preliminary understanding of a conductor. There are so many free electrons we are talking about. Okay, so many electrons are inside the conductor. Okay, and when there is one external field applied, what will happen? The free electrons will experience force, and these free electrons will try to redistribute itself, to move from there to. So these are negatively charged electrons, so already they will push each other. Okay, and they will redistribute on the surface. They will just push it apart. Okay, the maximum distance they will take, and they will actually settle on the edges. Okay, they will not leave the metal, but they will settle on the edges, these free electrons. And when they are settled there, even if you remove the electrostatic field, the external static field, or even if it is there, what happens? The electric field inside the conductor cancels out. So suppose there is electric field due to one electron on the edges on the left. So these electric fields are there, and from the right the electric fields will act like this. On the right side of electrons, the electric field will be like this, and they will cancel out. So total electric field will be 0 inside, and even particularly at a point, the electric field will be cancelled, or both the electric field due to all other free electrons will cancel each other, and there will be no electric field inside the conductor. This is what the first result is all about. So it says that even there is external field or no external field in the static situation, okay, when the charges are not moving, the free charge will distribute themselves, that the electric field is 0 everywhere inside. Okay, and this is electrostatic field is 0 inside a conductor. This is the result. Let's move to the second result, and that says at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. So the first result says that inside the conductor there is no electric field. Okay, and the second one is at the surface the direction of the electric field is normal to the surface, which simply means there is 90-degree angle between electric field and the surface. Okay, every side it is 90-degree. Okay, and if we take electric field in any other direction, let's say the tangential direction, if the electric field is something like this, then what will happen? Because of the tangential direction of the electric field, the electrons or the free charge carriers on the surface that we have already proved in the first result, which is there, will start moving. And when there is movement of charge happens, it simply means that it is not the equilibrium situation or the static situation, which contradicts whatever we are studying now. We are studying electrostatics of conductors. Okay, so when the charges are static, okay, and if we think about any other direction of electric field, then suppose we talked about the tangential direction of electric field, it simply means this electric field will exert some force on the charges on the surface of the conductor. Okay, and because of that force there will be movement of the charge, and when the charge will move it will not stay static, which contradicts the whole concept that this is electrostatics of the conductors. That's why we can say that on the surface, at the surface of a charged conductor, electrostatic field must be normal. Okay, must be normal to the surface at every point. All right. Our third result is the interior of a conductor can have no excess charge in the static situation. Very simple. We have already discussed this. If there is a conductor and even if there are free electrons inside, but because of these free electrons, they will exert force on each other, or even there are external electric fields, the forces will be exerted on each free electrons or the charge carriers, we say. And because of this force, and because all these electrons are negatively charged, they will just push each other. Like charges repel, they will push each other, and what will happen? All these free electrons will move to the farthest position, which is the surface. Okay, and because they will move to the surface, then we can say that inside the conductor, in the interior of the conductor, there will be no excess charge in a static situation, because after the movement happens, the charges will rest on the edges. Okay, it will just, after once they will have equilibrium. Maybe in the beginning they will move, but then they will just they will have a static situation. A static situation is called the equilibrium situation, when the forces will settle down and all these charges will be redistributed, and then we will see that there is no charge conductor, the free electrons inside the conductor. And we can prove the third result also by using Gauss's law. What does Gauss's law say is that flux is actually electric field multiplied by the surface element of the enclosed surface, that is actually equal to charge upon epsilon naught. So if we take any small surface element inside the conductor and we want to know what is the charge inside it, we know that inside the conductor electric field is zero. We have already proved it in the first result. It simply means that here E is 0, means whole electric flux is 0, and that simply says that the charge inside this implies that the charge inside the conductor is also 0. So that is Gauss's law. Gauss's law says that flux is equal to E multiplied by delta S, that is equal to charge upon epsilon naught. But we know that electric field inside the conductor is 0, which will say that the charge inside the conductor is also 0. And we have proved that there is no extra charge, excess charge inside the conductor in a static situation. Let's move to the fourth result, which says that electrostatic potential is constant throughout the volume of the conductor and has the same value as inside or on its surface. First, talk about the inside of the conductor. Okay, and we are talking about the electrostatic potential. So inside the conductor, we know that electric field is 0. We have already proved it. Okay, so that simply means that inside the conductor, there is no work done in moving the charge from here to any other point. Okay, because the electrostatic field is 0 there, so there is no tangential component of the force. Okay, so if there is no tangential component of the force, then the work done is actually there is no work done. Okay, so there is no work done. That simply means that the potential difference delta V is 0. There is no difference of potential. So potential is what? Constant value. That simply says that potential is constant inside the conductor. And the same we talked about on the surface we know that electric field is actually normal to the surface. So it is, if the electric field is normal to the surface and if it is not tangential, then we know that there is the tangential component of electric field is 0. Only the normal has some value, but tangential it is 0. It means the free electrons on the surface of the conductor will not move. Okay, so there will be no work done in moving over the surface, right? And in other words, we can say that since it has same potential on the surface, then moving the charge is, there is no work done in moving the charge, so there is no potential difference. Okay, so it's the same thing either way. So in that way we can say that even on the surface the potential is fixed. Okay, it is, potential has a fixed value, there is no potential difference on the surface. But the moment we go just a little bit far from the surface, then what happens? Potential at the surface and just outside the surface has different value. Why? Because there is electric field, okay, which is normal to the surface, which means as we go far from the surface, the value of electric field will affect the potential, because potential is actually, it is related to the electric field. And as we know, electric field is inversely proportional to 1 upon r square. So the electric field will change the moment we go farther from the conductor. We go more far, the electric field will be reduced. Okay, and if the electric field be reduced, so will it affect the potential. And that's why on the surface the potential is fixed, because electric field is fixed there, normal only in one direction. Inside it is fixed because the electric field is 0, so that's why our potential difference is 0. But if we go outside the conductor, then the potential will change. That's it. And also, to make it very clear, that when we say that the conductor, the metallic conductor is charged, we don't only mean that because there are free electrons it will be only be negatively charged. It can be positively charged as well, because there are ions inside metals as well. And what are these ions? When the electron leave the atoms, the free electrons, what we get after that, so these are loosely attached electrons that leave the atom, then whatever is left, the nucleus, okay, with some certain electrons will be left, and these are called ions. So these ions will be there, and these ions are actually positively charged ions, right? So that's why the metal, what we talked about, the conductor, can be positively charged as well. And now whatever results or whatever topics we'll cover, it will have both kind of charges, positive and negative. Let's come to the fifth result, the important one, that says that electric field at the surface of a charged conductor is actually equal to sigma upon epsilon naught. So, and that is multiplied by the unit vector n. N is the normal direction of the electric field to the surface. Now to derive this formula, E is equal to sigma upon epsilon naught multiplied by unit vector n, we will be using the Gauss's law. And what are we actually deriving? That electric field at the surface of a charged conductor. Okay, so to do that, we are going to use a pillbox. What is a pillbox? It is a kind of a short cylinder that we make inside, inside the conductor. So some portion of this cylinder is outside the surface of the conductor. Okay, this is outside, and some portion is inside. And simultaneously we use the Gauss's law. And what does Gauss's law say? Says that electric flux is actually equal to electric field and dot delta S, and where delta is the area vector and E is the electric field, and this is the dot product. Or if we just focus on the magnitude, we will say E is equal to phi is equal to E delta S. Now, as we can see in the picture here, figure, the area element, this is delta S, has a direction, and that direction is normal to the surface, right? And that makes it E dot delta S is equal to E delta S cos theta. And the angle between delta S and electric field is 0 degree. So cos 0 degree is equal to 1, and then we can say that our flux through this surface, what you can see in the figure, is E delta S. This pillbox is used just to use the Gauss's law to prove or to derive at the formula for electric field at the surface of a charged conductor, nothing else. And it has certain meanings. Let's see what other important things are there when we talk about the this pillbox and the Gaussian surface attached to it. So here the Gaussian surface has another surface which is the curved, these round surfaces, okay, of the cylinder, the round surfaces of the cylinder, which is outside the conductor. And we can also talk about what is the flux through these surfaces. So the direction of this curved surface here is something like tangent to the conductor, okay? And we know that electric field is only normal to the conductor, that we have already proved earlier, that electric field on the surface is only normal to the conductor. And the area surface direction for the curved surface is tangent. So the angle between electric field and the area vector for the curved surface is 90 degree. So that's why the flux will be 0. And the only flux that will work here is through the through the surface, what we can see in the figure, which has normal direction, okay? And further, when we apply the Gauss's law, then we will see that the flux is actually equal to charge upon epsilon naught, okay? Now our charge is actually sigma multiplied by delta S, and sigma is the charge density, and we know that sigma is actually charge upon delta Q. Let's say small charge enclosed in that surface area, small surface area. So sigma is actually delta Q upon delta S, okay? So instead of Q here, because flux says that flux is equal to Q upon epsilon naught from the Gauss's law, and this is the formula for the flux. And when we equate this, then we find that we can replace Q by sigma multiplied by delta S, okay, here. And we can cancel out delta S both sides, and what is left is E is equal to mod sigma upon epsilon naught. And since E is an electric field, we need to give one direction, and we know that direction is only radially outward, and that is normal, not radially outward, I would say the normal to the surface. This was already proved, so this is our derivation of electric field on at the surface of a charged conductor. And the last result and last topic is electrostatic shielding, which talks about creating or exploiting the concept that the charge is always accumulated, the free charge is always accumulated on the surface, okay, not inside the conductor. So if we keep our conductor hollow, it means charges will always be accumulated on the edges, okay, and even there is no potential difference on the edges as well, okay. And inside the conductor, or if we make it hollow, we know that E is equal to 0 inside the conductor. So if we make it hollow, E is 0. Delta V, change in potential, is 0. So there is no change in potential, there is no electric field, so there will be no flow of electricity, and there will be no electric shocks possible inside the hollow thing, and that is called electrostatic shielding. So as the NCERT book says that the electric field, so what happens here, the electric field inside the cavity is 0 if you make the cavity, and whatever be the size and shape of the cavity, and whatever be the charge on the conductor, the external fields in which it might be placed, whatever you place it, but inside the cavity, because we have proved that inside a conductor the electric field is 0, and if we really make it hollow, then there is no flow of charge also, there is not a single time the flow of charge will be there, because these are empty spaces, right, inside. So inside these are the empty spaces, and there will be no electric field, and there will be no potential difference. And then very much applied in electronics and telecommunication and in many other fields. So what happens actually, whatever be the charge and field configuration outside, any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always 0. This is known as electrostatic shielding, okay, and this is used to keep safe the sensitive instruments, okay, in electrical supplies or in electrical network. So this concept can be used very effectively in protecting sensitive instrument. And that is it. Next time we will be covering dielectrics and polarization. So thank you.